This is the UNCC Work Artificial Intelligence for Powered Augmented Reality for Workers Senior Design Project presented by Damian Hupka, Zachary Zaleski, Duncan Tennant, William Clampett, Nathan Pecoraro, and our supporters Dr. Hamed Tabki and Dr. Nabila Busaba. The goal of this project is to use a camera and artificial intelligence to implement real-time vehicle detection. We would also like to create a mobile application for health tracking, and we would like to develop back-end communication between all devices and make that implementation scalable.
The project requirements were a few performance specifications. Most importantly, we wanted the latency to be less than 10 milliseconds, so we have the fastest possible reaction time for our workers. And we also had a goal to at least reach 10 FPS image processing for the completed AI implementation.
So the equipment used for this project are the NVIDIA Jetson AGX embedded board, Vuzix augmented reality glasses, a Samsung Galaxy smartwatch, and a TP-Link wireless AX1500 access point, which uses the 802.11ax protocol.
For our senior design project, our design options are using a client-server communication scheme using a WLAN network, or using a peer-to-peer communication between the Xavier board and any number of nodes within our system.
Our current design is having the goggles and Xavier board communicate using the client-server model we described. We're hoping to use a similar concept to get the wristband and Xavier board to communicate properly. Our app at the moment has a basic login and splash screen scene that we can use to aggregate the data from the rest of our server.
So here we have our communication flow graph. The NVIDIA Jetson will communicate directly with the camera via a wired connection, and from there, the Jetson will communicate with the augmented reality glasses, wristband, and mobile app via an access point utilizing the 802.11ax protocol.
So here's a brief code overview of the latency testing with the client-to-server implementation. We run this test 500 times in order to gain an accurate understanding of the average latency we're measuring. In this example, the board is sending a message to the AR goggles, and the goggles will return the same message. This is used in calculating the round-trip time to measure the latency of the implementation.
The following graphic below represents a visual representation of our project. As you can see, the camera is overlooking the client that is wearing the goggles and also the smartwatch, while being within range of our Xavier board.
Here's an overview of what we plan to accomplish next semester in order to have a completed back-end communication scheme and end-user app to measure characteristics of the system by May. We plan to complete implementation of communication between every device, finish development of camera AI for vehicle trajectory prediction, and implement the system in such a way that multiple wearable devices can communicate and operate concurrently.